Take two. The idea of derivatives. Get used to derivatives. We will be dealing with derivatives up until, let's see here. Maybe Valentine's Day. Maybe a little bit further than that. Into February. Maybe through February. We'll be dealing with derivatives. The next two chapters are the basis of everything in regards to moving forward in the calculus world, the idea of derivatives. By the time we get done with derivatives, you will be sick and tired of derivatives because we're going to be doing so many different derivatives, techniques of derivatives. The hope is, once again, sometime in the beginning, the first couple weeks of February, we should be done with them. That's the hope. That's the hope. It depends on how many days we're around. So, the idea of derivatives. When you deal with a derivative, you're talking about a rate. When you're talking about derivatives, you're talking about a rate. How fast something's occurring. Velocity, acceleration, rate of chemical reactions, slopes. These are all rates. And believe it or not, we've dealt with derivatives already. We just didn't call it a derivative. Didn't call it a derivative. All I asked you to do was determine the slope of the tangent line of y equals x squared at x equals 3. Well, slopes are up here in the categories of derivatives. So if we remember back to our slope of the tangent line, how we determine the slope of a tangent line? Limit as x approaches a of f of x minus f of a over x minus a. Go ahead and determine the slope of the tangent line. Hopefully there's no ooh and ah like, ooh, I don't quite remember that one. Should be fresh in your brain. Dylan, what do you come down to? Negative 3? 6? There we go. Should get a value of 6. And once again, this is the slope of our tangent line at x equals 3. The slope of our tangent line at x equals 3. What this is also called, it is also called the value of our derivative of our function at x equals 3. There is a double meaning to this. Yes, it's the slope of the tangent line at x equals 3. It is also the value of the derivative of f of x at x equals 3. We've done derivatives already. We've done values of derivatives. We just didn't call them that. We just said, well, what's the slope of the tangent line? And we looked at delta y over delta x as x gets closer to our specific value, and we found the slope of the tangent line. We were a delta epsilon away. So we've done these. We just never called them derivatives. Notations for derivatives of f of x for a function or y. Okay, how we denote derivatives is we put a little prime in there, f prime at x. The derivative of f of x is f prime at x. So what we calculated up here, the value of our derivative, what we calculated here, our slope was the value of our derivative at 3. So the notation we have is f prime at 3. The value of our derivative at 3, f prime at 3 was a value of 6, which is the slope of our tangent line. So whenever you see the little hash in there, that means we're dealing with the derivative. Another way of writing that would be f prime at 3. A little prime mark up there, little hashtag. No, not hashtag, but prime. Others. We can just deal with a y prime. We can deal with a y prime. We have dy over dx, or just d dx. Our slope is delta y over delta x. And what the d comes from is they just use the first letter for delta. This is the derivative of y with respect to x. So when you deal with this right here, dy dx, this is the derivative of y. We're taking the derivative of y with respect to x, which means we're going to develop all these rules with respect to derivatives. X just tells us what is the independent variable that is there, that we're going to apply the rules for, too. This is the independent variable to the relation. That's the independent variable. It's y equals x cubed plus 3x squared minus 7x plus 4. It's my variable that's in here that we're going to apply our rules to. The y on top tells us what equation we're dealing with. We're dealing with the equation y equals. And the variables that are in the equation y equals are all the x variables. Using this notation, we can go y prime at 3, we can go dy dx, and have a little subscript here, x equals 3. Okay, that is all the derivative. The derivative at the value 3, we could signify with either of these. The derivative of y with respect to x at x equals 3, or my function value, my derivative of my function at 3. Given the function x squared plus 2x minus 6, find g prime at 3. Find g prime at 3. Well, now I'm dealing with g there, so I'm going to change my variable to g. My g prime at 3, my g prime at a is limit is x approaches a at g of a, x minus g of a over x minus a. Once again, we'll go back to the idea of our delta y over delta x. When we find a value, When you find a value, just think of it, I'm finding the slope of a tangent line. I'm just finding the slope of the tangent line. There's nothing different except for the verbiage here. It's like dealing with arc length and radians. You're finding radian, you're finding arc length. When you're finding arc length, you're finding the radians. It's the same idea here. Evan, what do you come down to? Well, these cancel, evaluating, we have a value of 12. So we have G prime at a value of 5 is equal to 12. When you're trying to find values of the derivatives, by definition, this is by definition, think of the slope of the tangent line. Slope of the tangent line. Where the challenge starts to come in is when we take and we want to determine a general derivative. This is a general derivative, which means you're going to come back into just a function notation. You'll come back into a function notation. You won't have an exact number value here. Well, we have two different ways. We have the difference quotient, or both of these are difference quotients. I'm still fairly impartial to this one here because I still like utilizing this because to me it's easier to factor and cancel and sub rather than to build up and deal with my difference quotient over there. But either way is the correct way of dealing with this. I want to find the general derivative, which means I want to leave things in terms of x here. Okay, I don't want a specific value. So if we take a look, we have the limit as t is approaching x. We'll go both ways here, just to show you that you can do it either way. The limit as t is approaching x of f of t minus f of x over t minus x. It looks very similar, but rather than substituting in a number at the end, we're substituting in x for t. We're putting x in for t. So we have the limit as t is approaching x of f of t, which means wherever I see an x, I'm putting in a t. So we have t squared plus 5 minus our f of x, or g of x, does not matter. X squared plus 5, and this is over t minus x. We evaluated t, subtract out the evaluation of the x over t minus x, which is the limit as t is approaching x of t squared plus 5 minus x squared minus 5 over t minus x. The nice thing about this, all your constants will always continue to cancel out. So the plus 5 minus 5 go bye-bye, leaving us with t squared minus x squared. Well, if I take t squared minus x squared and factor that down, Brandon, what does that factor to?
Is it t plus x, t minus x?
That's correct. And once again, just like before, this t minus x factor, you're going to be able to cancel this out each time. It's a discontinuity that you're going to be able to remove. So the t minus x's, they move to Texas. And then we can substitute in x for t. So we have x plus another x, which gives us 2x. So g prime at x is equal to 2x. Now if we use the other technique, the difference quotient up here, we have the limit as h approaches 0. My function being evaluated at x plus h. So we have x plus h squared plus 5 minus my function, which is x squared plus 5. All over h. And once again, if you use this technique, and this is a technique that is almost referred to by colleges, I don't know, a lot of, even by our book, they go this method first and then they say, oh, by the way, if you want to use the other method, use the other method. I like the other method. That's just me. Because this makes us expand out x plus h squared, x plus h cubed, x plus h to the fourth, which could be a lot of work. But if I expand this out, we have x squared plus 2xh plus h squared. If you use this technique, I would suggest that you memorize that. Plus 5, and then minus x squared minus 5, and this is all over h. The x squareds, they cancel out. The plus 5 and the minus 5 will cancel. And what you'll see each time is this function here will always cancel out with terms in the front. So we're left with the limit as h approaches 0 of 2xh plus h squared over h. We can cancel an h out of all three terms. So we're left with 2x plus 0 or a value of 2x. So either one will give us the same solution. And both of them, we'll use both of these to make derivations and deal with derivations of derivatives. But if I go to my next one here, if I use my second technique with this next one, I'm going to have to multiply by conjugates then and deal with the multiplication of conjugates, which, you know, to me, I don't know. Get a little squirmish with those. Limit as t is approaching x. You finish out f of t minus f of x over t minus x. and you factor down the bottom. Then what's the bottom factor to?
Square root of t plus square root of x, square root of t minus square root of x.
And the square root of x's, or t minus x's, and move to Texas. So we're left with 1 over, putting in x for t, square root of x plus square root of x. Square root of x plus square root of x, Nate, would equal what?
2 square root of x.
2 square root of x. Once again, if you plugged in the other one, we have square root of x plus h minus square root of x over a value of h. And what you would have to do is you would have to multiply by a conjugate, square root of x plus h plus the square root of x. And then you'd have to work through. Once again, I like to factor a little bit better. We look at the next one. Limit c is approaching x. F of t minus f of x over t minus x. You have a complex fraction multiplied by your common denominator. Once again, this is going to be this is a challenge to all your algebraic skills that you learn. Multiply top and bottom by your dx. Would not multiply through by that, I just keep it as tx. Factor out a -6 on top, so you can switch that around. And then your t minus x's, they move to Texas. Putting your x in for t. -6 over x times x, or -6 over x squared. If a function has a derivative at x equals c, it's guaranteed that it is continuous at x equals c then. You have no discontinuity at x equals c. If you can find the value of a derivative at c of a function, you're guaranteed to be continuous at that value then. You have no discontinuities, you have no vertical asymptotes, you have no open dots. Problems you run into, with derivatives, when you have corners, when you have cusps, those are cusps, vertical tangent lines, discontinuities, that's where you start running into problems with derivatives. I gave you a worksheet. Worksheet is just basically doing general derivatives, and your general derivatives are on the front. On the back, you have values of the derivative. And then I doing a couple equations with tangent lines. Problem number 3. On problem number 3, you're going to have to use the limit as h approaches 0. As x approaches, you have to use the first one here, h approaches 0, f of x plus h minus f of x over h. So on number 3, you'll have to utilize this one. When you find derivatives of trig functions, we'll have to use that definition also. Questions? Once again, derivatives will be here for a while. We'll be discussing a lot of different things with respect to derivatives. And that's the basis of Calc 1. Limits, derivatives,